Okay, my dear students, so welcome back. Today we are going to solve one question on heat equation. Already I have written one question here, which let us read first. So, what is the situation? We are talking about one dimensional heat flow in a rod or bar, whatever you want, you can call it. Okay, so one bar is there, and let us keep it at along x-axis. Okay, and this is your y-axis. Fine, this is your origin. Okay, and heat is flowing through this bar, and the question is as follows: heat flows through a uniform bar of length 5 centimeters. So this length here is 5. Okay, so suppose that the temperature U, so temperature we are denoting by U, and if you observe here, they are taking U as a function of xt. Is it fine? Of course it is fine. Suppose at any point in the bar you want to talk about the temperature. Of course, the temperature will depend on the position of this point, which will be x, right? Because we have placed the bar along the x-axis. So x coordinate will give us the position. So u, or the temperature, will definitely depend on the position, which is x, and of course at what time you are talking about, right? So u, that is the temperature, will be a function of x and t. So u, the temperature, will be a function of the position on the bar and the time. So looks good. Suppose that the temperature uxt in the bar is determined by the following boundary value problem. One equation is given to you, and x lies between 0 and 5. Of course, you have taken the length of the bar as 5, and the time is positive, which is always true. Subject to, now these are the boundary conditions. What is the meaning? Just quickly let us have a look at it. U0t, 0t means the x value is 0, right? It means u0t is equal to 0. u0t, which point they are talking about? They are talking about this end, right? And u5t, u5t means x is equal to 5. It means they are talking about the other end. So what is this condition? That u0t, temperature at this end, and u5t, the temperature at this end. At both these ends, at both ends of the bar, the temperature is equal to 0. Okay. And the other condition is the initial condition, the second one, that ux0, it means the temperature at any position x at time t equal to 0. This is our time, right? So the temperature at any position x on the bar at time t equal to 0 is given by a function which is same as x. Depending on the question, this function may change. Here they have given x. They may, in some other question, this x may be some other function, x square, x times 5 minus x, or whatever. Okay. So here we have taken the function as x. So ux0 is equal to x. So this is the initial condition which they have given. Of course, x lies between 0 and 5. That's fine. Find the temperature distribution in the bar at any time t. Now let us solve this heat equation. Suppose the solution of this equation is equal to some function of x multiplied by some function of t. Capital X is a function of x and capital T is a function of t, where small x is the position and small t is the time, right? Now, because this is a solution of my given equation, it means that this solution should satisfy the given equation. K dou square u by dou x square is equal to dou u by dou t. So if I put this value of u in my given equation, what will I get? This implies K. Now see, what is the left side of the equation? The left side of the equation is the second derivative of u with respect to x. Second derivative of u partially with respect to x, right? So it means that this t, which is a function of t, will not get affected. It will remain as it is. And we will differentiate only x function 2 times partially with respect to small x. So that will give me x double prime is equal to the right side. The right side of this equation is dou u by dou t. It means we have to differentiate partially with respect to t. So if I differentiate this thing partially with respect to t, what is the meaning? Meaning is that x, because it is a function of small x alone, it will not be affected. Only we have to differentiate t with respect to small t. How many times? Only one times. Partial derivative of u with respect to t. One time only, right? First derivative, first partial derivative of u with respect to t. So x will not get affected and t will be differentiated one time. So this is what I am getting when I substitute my solution in the given equation. Now, how can I write this? I can separate all x on one side and I can shift all t on other side. No problem in doing that. And now, after doing this, let us say that this ratio is equal to sum minus lambda. Suppose. Okay. Now, what is the next step? From here, I will get two equations. One equation will be x double prime divided by x is equal to minus lambda. And second equation which I will get will be t prime divided by kt is equal to minus lambda. From the first one, I will get x double prime is equal to minus lambda x, or you can simply write it as plus lambda x will be equal to 0. And from here, we will get t prime is equal to minus lambda kt, or you can simply write it as plus lambda kt is equal to 0. Let us do one thing. Let us call this equation, this solution which we have supposed, let us call this equation as 1. Let us call this equation as equation 2, and let us call this equation as equation 3. Okay. Now, one more thing before we proceed, one more thing we want to do. These conditions are given to us. Let us see what we get from here. Okay, I am not able to cut it. I don't know why this is happening. Anyway, no problem. So we have the given conditions the boundary value conditions. Okay, the boundary conditions. What are the boundary conditions which are given? So u0t is 0. This is number 1. Okay, and another one is u5t is also 0, right? And our solution is of the form uxt, which is equal to x as a function of x and t as a function of t. Okay, now if I put x equal to 0, what will I get? I will get u0t is equal to x times 0 and t times t. Okay, x 0 times t. Okay, and this value should be equal to 0 according to the boundary condition, right? Now, what is the meaning? This gives me that x0 should be equal to 0. Okay, now same thing, let us go to the second boundary condition. Again, my solution is in the form uxt is equal to x, which is a function of x, multiplied by t, which is a function of t. Now, when I put x equal to 5, what will happen? u5t will be equal to x times 5 and t, which is a function of t, so that will not get affected. And this value should be equal to 0. This again gives me that x at 5 should be equal to 0. So using the two boundary conditions which were given in the question, we have obtained another two conditions which may be useful for us. Okay, looks good. Now, let us start focusing on equation number 2 and equation number 3. So first we will deal with equation number 2, and when we are solving equation number 2, we will try to make use of these conditions which we have obtained for the function capital X. Okay, so let's start with equation 2. Let me try if that cut function is working here, because there I think it is an image, that is why it was not cutting. Yes, I think here it is working well. So let me drag it here. Yes, perfect. Okay, good. So now, okay. What we remember when we see this equation number 2, see, this equation is reminding us of the Sturm-Liouville eigenvalue problem. So we discussed 3 cases when we talk about the Sturm-Liouville eigenvalue problem. 3 cases we have to consider. The first case is that this lambda can be equal to 0. Second case is lambda can be less than 0. Lambda can be negative. But the Sturm-Liouville eigenvalue problem discussion tells us that both these cases will give us a trivial solution. Only when I have lambda which is positive, let us say a lambda equal to some alpha square. Okay, so this case only gives us a non-trivial solution of equation number 2. So these 2 cases we will not consider. We will consider the lambda greater than 0 case, where we are getting a non-trivial solution. And in this case, the Sturm-Liouville eigenvalue problem discussion also led us to this solution, that x will be equal to C1 cosine alpha x plus C2 sine alpha x. So all these things are coming from the Sturm-Liouville eigenvalue problem. So this is my non-trivial solution of equation number 2. Now, just now we have obtained 2 wonderful conditions which we are going to use now. If you see the first one, that x at 0 is equal to 0. Let us use this in our equation which we have written just now. Let us call it as equation number 4. Okay. So using this condition in equation number 4, what we get? X0, So if I put small x as 0, I will get C1 cosine 0 plus C2 sine 0, and this should be equal to 0, right? Okay, what this gives us? That C1 cosine 0 is 1. So C1 plus C2 sine 0, that will be 0. So this gives me directly that C1 is equal to 0. Now what happens to my x? Therefore, x, this solution now becomes, the first part will become 0 because we have evaluated C1 to be 0. So x will be only C2 sine alpha x. Okay. Now let us see if we can do anything else. Yes, we can do, because we have another wonderful equation which we are going to use. Another useful condition, that x5 is also equal to 0. Let's use it. X at 5 is also equal to 0. So when we put x equal to 5 here, what we get? X5 is equal to C2 sine x is 5. So 5 times alpha, right? And this should be equal to 0. Okay. Now, this leads to two options. First option can be that C2 is 0. Second option can be that sine 5 alpha can be equal to 0. Okay. Now, is it possible? No. Why not? Because we are talking about a non-trivial solution, which should be a non-zero solution actually, isn't it? C1 already you have got as 0. If you take C2 also as 0, this solution will become 0, which will be a trivial solution, right? But we have a non-trivial solution in this case, isn't it? So it means that this case, that C2 is also 0, is not possible. So we will reject this possibility. So what are we left with? We are left with sine 5 alpha should be equal to 0. And this gives me, using simple trigonometric formulas and rules and all, simply we get that 5 alpha should be equal to n pi. And this gives me that alpha will be n pi over 5. So another condition we have obtained now. So finally, I can write that therefore my solution xx is equal to C2 sine alpha x. Alpha value you have obtained just now, n pi by 5. Sure. So it will be n pi x by 5. So this is my capital X. Now, same way, after dealing with equation number 2, we have solved already equation number 2. Now, let me deal with equation number 3. So again, let me try to copy this from here. Okay, done. Now let us deal with equation number 3. Equation number 3, I will not go into much detail because this is a simple variable separable differential equation, right? So this I will leave it to you because this is a simple variable separable differential equation. You have to separate t with the other variable, the capital T, you have to separate with the small t, right? And after separating capital T with small t, you will integrate both sides, and you know how to integrate that. And after integration, you will get the solution. So I am writing the solution directly here, that my function t will be obtained as some constant c3 e to the power minus lambda k t, or simply you can write it as c3 e to the power minus lambda, we have substituted as alpha square, right? Because we have taken the case that lambda should be positive. So lambda we decided to keep it as alpha square. So this will be alpha square kt, and we have already evaluated the value of alpha, which was n pi by 5. So this will become e to the power minus n square pi square kt by 5 square. I am writing it as 5 square. You can write it as 25 also. That's not a problem. So we have obtained capital T, and we have also obtained capital X. Now we are in a good position to write our solution u x t will be equal to c2, because uxt is actually equal to x multiplied by t, and both these values you have evaluated. Okay, so we are putting the values of capital X and capital T. So that will be c2 sine n by x over 5 multiplied by capital T, that is c3 e to the power minus n square pi square kt divided by 5 square. So this is our solution u, which is a function of x and t. Another thing here of importance is that n can take the values from 1, 2, 3 and so on, right? So what we do here, we write it as sine n pi x divided by 5 e to the power minus n square pi square kt divided by 5 square, and C2, C3, C2 multiplied by C3 will be another constant, which we will denote by some an. Another thing which we have to do, which we have to consider, and we will write that the most appropriate solution is uxt is equal to an sine n pi x over 5 e to the power minus n square pi square kt divided by 5 square. And we will consider a series where n ranges from 1 to infinity. So this is our most appropriate solution. Still, what remains to be done? That we have to find the value of our an. Now, before going to that, there is one initial condition which is given in the question, which was given as ux0 is equal to x. Now, what will happen if I substitute t equal to 0 in this series? We will get ux0 is equal to summation an sine n pi x divided by 5 e to the power, when you put t equal to 0, this will become e to the power 0, which is equal to 1. And this value should be equal to x, right? So we are getting summation an sine n pi x over 5 is equal to x, which takes us back to half range Fourier series. And from the half range Fourier series formula, we will write that an will be equal to 2 divided by 5 integral 0 to 5 fx sine n pi x over 5 dx, and here my function fx is equal to x. So I will write here x. We know how to integrate this. Let us integrate and finish our answer. This will be equal to 2 by 5 x sine n pi x over 5. Many times we have done integration by parts, so you know how to do it. I am writing it directly. I am sure all of you are capable enough to do this integration by yourself. So you will get minus x cosine n pi x divided by 5 divided by n pi over 5. And another term which you will get will be minus sine n pi x over 5 divided by n pi by 5, and another n pi by 5 will come, so it will become n square pi square over 5 square over the limits 0, 5. And this gives us 2 over 5. If you check this second term, when you put x equal to 5, this will become n pi 5 over 5. So 5 and 5 will cancel, so it will become n pi. And we know that sine n pi is equal to 0. And when you put x equal to 0, again you will get sine n pi 0 over 5, right? So that will become sine 0, and sine 0 is also 0. So in both cases, this second term will become 0. So we can cancel it directly. And this term is a constant, so you can shift it outside the bracket, right? If you want to keep it inside, keep it as it is, no problem. So this will become minus 5 cosine n pi 5 over 5 and so this is the first term minus, now we will put x equal to 0. So when you put x equal to 0, so this will become 0, so everything will become 0. And here this n pi by 5, you are shifting it outside, so it will become 5 over n pi. And if you want to cancel some things, this 5 will cancel this 5, and this 5 inside the angle will cancel the denominator. So what are we getting now? We are getting 2 over n pi minus 5 cosine n pi, and cosine n pi is minus 1 to the power n. So this is the value of an which you have calculated. So if you want to write the solution, we can, let us drag it downwards and we will write the answer. Yeah, looks good. So this uxt will be given as okay, some technical issue. That's okay, that's normal with online teaching. Okay, so our final answer will be is equal to summation an, which you have already evaluated now in this light blue color. So that will be 2 over n pi minus 5 times minus 1 power n. This is my an. Then sine n pi x over 5 e to the power minus n square pi square kt divided by 5 square. So this is the solution of our heat equation. I hope I could do some justice explaining this problem, and I hope all of you understood it. And this is all for today's video, and we will meet again very soon with some new topic. Okay, that's all. Take care, all of you. Goodbye.